and it's my pleasure to be here to talk to you today on mechanism-based molecular design of chemical with a lower carcinogenic potential. As you know, cancer is one of the leading causes of death in the US and in the world, and it was estimated about 90% of the death of the human cancer are linked to environmental, dietary, or behavior factors, as shown in this pie chart here. And this slide lists all the known human carcinogens that are classified by the International Agency for Research on Cancer, or IARC, and except for a few bacteria or virus, which are biological carcinogen, and the radiation, of course, is physical. Most of these carcinogens that cause cancer in humans are chemicals. In the new chemical program of the EPA, U.S. Environmental Protection Agency, the Toxic Substance Control Act requires a manufacturer or importer of a new chemical to submit something called pre-manufacture notification to EPA 90 days before they intended to manufacture or market or import this substance. And during the 90 days, the EPA will review all the data they submitted, and which includes the chemical identity and what the production volume they anticipated, the byproduct or some exposure information. But unfortunately, EPA do not require them to submit toxicity data. So the toxicity data is very limited. And each year, EPA receives about 1,000 new chemical PMN application, and without carcinogenicity data, EPA rely on something called mechanism-based sexual activity relationship analysis to evaluate the carcinogenic potential of the chemicals. And basically, what they do is to find out what's the mechanism of the existing chemical that are carcinogen, and look at the physical chemical property and the metabolism, and then compare that with the chemical without any data. And over the last 2 decades, EPA have collected data and conducted SAR analysis on about 30 chemical classes or subclasses, as shown here. And what we do is we look at class by class, look at how some of the chemical in this class are carcinogenic and some are not, and what the structural feature that contribute to the carcinogenicity of the chemical. And chemical carcinogen can be broadly classified as genotoxic and non-genotoxic carcinogen. And genotoxic carcinogen, basically they can interact directly with DNA, or they are also called DNA reactive carcinogen. And on the other hand, the non-genotoxic carcinogens, they don't interact directly with DNA, and they may, some of them act through like receptor binding the receptor or oxidative stress. In the early 50s, based on the pioneer work of the Millers, Dr. James and Elizabeth Miller at the Mercado Laboratory on Cancer Research, University of Wisconsin, they developed the concept that electrophilic are the ultimate carcinogen to interact with DNA to initiate carcinogenesis. And since then, the concept of electrophile has been the most probable rationale for the carcinogenic action of many chemical carcinogens. And this table just shows some example of the electrophilic species which are the possible or ultimate carcinogen of a variety of them chemical carcinogen. And and some of the common encounter electrophilic species are shown in here, which include carbonium I, nitronium I, and epoxide. And and virtually all genotoxic carcinogens, either spontaneously or through after metabolic activation, generate electrophilic species. They bind covalently to the nucleophilic site of DNA, as shown here. But although a chemical that contains or has the potential to generate electrophiles, it doesn't mean that they are always carcinogenic. There are a lot of factors that you have to consider. For example, is the nature of the electrophile, and consider their reactivity and whether they can be there's resonance stabilization of the electrophile, and how flexible they are, and whether they're polyfunctional or the space between the two reactive groups. And it's also very important to look at the environment of the surrounding electrophile. There's the rest of the chemical. Or enter?
Just try enter. See that works.
Oh.
You see?
Oh, okay. And then move it back. Okay, go back. Okay. Okay, maybe that's better. Okay, and because the rest of the chemical can affect the physical chemical property of the molecule, like the molecular size and shape, and also which can affect the absorption, activation, or detoxification of the chemical. For compounds which require metabolic activation, resonance stabilization of the electrophile is very important, because these electrophilic intermediates are very reactive, and they are readily hydrolyzed or detoxified. The resonance stabilization can give this reactive intermediate a longer life span, so that they allow them to remain reactive during the transport from the site of activation to the target macromolecules in the nucleus, like the DNA. I mentioned about the molecular size and shape are important. As shown here, for example, that this on the left-hand side, this is a benzapyrene, a polycyclic aromatic compound, and okay, here. And virtually all of the potent pH angular compound with about 4 to 6 benzyl ring. And on the other hand, all the non-carcinogenic pH have a structure that have highly elongated or highly symmetric. So while this one is carcinogenic, this one, which is highly elongated, is not carcinogenic. And also the substituent effect, they can affect the solubility of the chemical. And with chemicals which are highly hydrophilic or highly soluble, not readily to be absorbed by oral or thermal route, and even though they are absorbed, they will be excreted rapidly, so that they are not bioavailable. So on the left-hand side, this 4,4-diamino stilbene is carcinogenic, but after introduce the hydrophilic group like sulfonyl group to the compound, then it abolish the carcinogenicity. And for the molecular flexibility and the polyfunctionality is also important. For example, the epoxide here attached to a aliphatic cyclic structure, which is very rigid and is not carcinogenic. But if it's attached to a aliphatic linear structure, make it more flexible, it is carcinogenic. And diepoxide are more carcinogenic than monocarcinogenic. And with the knowledge of the structural feature that can affect the carcinogenicity of compound, we can use it to reduce the carcinogenic potential using some of these general approaches for all chemicals. For example, you can introduce a bulky group to increase the molecular size. Like in general, it's about 1,000 is the cutoff. If it's lower than you need, you can increase it, make it bigger, or introduce hydrophilic group and like sulfonyl group or carboxyl group. In that way, to reduce the bioavailability of the chemical and make it less absorbed and or not to be bioactivated. Or you can introduce substituent adjacent to the electro group to exert electronic or steric effect on the bioactivation of the compound. And for alkylating agent, if you can use a higher than like 4 carbon butyl group, usually it's the methyl group. The smaller the alkyl group, the higher alkylating activity it is. And also, you can also position the electrophilic functional group in the middle, let it less flexible instead of at the terminal position. And also, you can, for chemical, they require metabolic activation, and so avoid the structure feature that allow them to be stabilized by resonance stabilization. And so these are some of the general approaches that you can use to decrease the carcinogenic potential of chemical. And there's also specific approach for specific class of chemical. I will give a few examples. And these are polycyclic PAH, polycyclic aromatic hydrocarbon, and many of them are carcinogenic. I mentioned that usually 4 to 6 benzene fused together with that are not elongated in structure. This just shows the incumbent, they call incumbent area of a methylcholandrine by measuring the distance, the bond distance, the length, the size, and then with a rectangular, and look at this area to measure the size. And it has been shown that for all the potent pH carcinogenic pH, the incumbent area is between 100 to about 150 angstrom, and smaller than 100 and larger than 150, they are not carcinogenic. And the reason that angular structure, some angular are carcinogenic, because they have something called a Bay region or a foil region. And these are important because the metabolic activation to the Bay region or foil region, diol epoxide, as shown below, are the key metabolic pathway for the carcinogenesis or pH. And you notice there's also a region called L region. The L region is a detoxification site. If it's blocked, then it will enhance the carcinogenicity. So this summarizes some of the knowledge we found out from SAR and mechanism analysis of pH. And like the molecular side, you can we know that the effect, the carcinogenic effect, decrease if the incumbent area is larger than 100 and less 150, and also the shape, if linear, elongated, then the carcinogen will be also low, and then also you can also reduce the carcinogen activity by substitute at the bay or foil region, so that prevent them from forming the electrophilic intermediate. And as I mentioned, for the L region, you introduce a small alkyl group like a methyl group, it will increase the carcinogen because it prevents the detoxification. But you don't want to introduce too big a group, otherwise, increase overall size of the chemical. And so with understanding about this structural feature that affect carcinogen, we can design pH that with low carcinogen by modifying that side, make it less than 100 and 150 in incumbent area, and avoid a compound with a bay region or a foil region. If such a region is absolutely needed, then you can put substituent near or at each of them, so that so that they don't allow to have the activate to form the electrophile. Okay, and then avoid to put methyl group, a small substituent at the L region. And another example I can tell you is about aromatic amines. Aromatic amines, there's a number of them are non-human carcinogens, just like benzidine or beta-nephthalamine, and there's a lot of them has been tested for carcinogenicity. So carcinogenicity data are available for SAR analysis of aromatic amine with different range structure, and also with different substituent at different position. We know which one is what the substitution at what position, and can more carcinoid than another. So analyzing all this data, we found out there's several factors, that can affect the carcinogen, like the number of reactor rank, the molecular size and shape, the number and position of aminogenicity group, and so on. Okay, and then also it's interesting that all these structural features that we found that can affect carcinogen also can influence the metabolic activation of the compound, and the metabolic activation of aromatic has been well studied. It's been shown to be a two-state phenomenon. The first one is either hydroxylated or acetylation, and then the second is the phase 2 metabolism, and ultimately found in nitronium I, then bind to DNA. And this one showed that study on 2, 3, and 4 isomer of 4 amino biphenyl has a very good correlation between mutagenicity, carcinogenicity, and the capability of the chemical to for hydroxylation, and then the planarity of the structure. And 3 and 4 isomer are planar, and they and 3 is a weak carcinogen, and this one is a very potent carcinogen, and they can also be N-isotylated and shown to be anhydrous. But introducing this amino group at the 2 position make the structure not non-planar, and being non-planar, it cannot be activated. They cannot find any anhydrosylate in the mediate, so it cannot be anhydrosylate, and it's not mutagenic and carcinogenic. And so this the knowledge we gain from analyzing what the structure can increase or decrease the activity. And then with that knowledge again, we can use these approaches to reduce the carcinogen of aromatic amine. And the last one is nitrosamine. Nitrosamine is very important to have, based on the biomedical mechanism, is the alpha hydrogen. It's very important. So the data have shown that this free chemical, the top one has 2 alpha hydrogen, and is a very potent carcinogen. This one is less, with only 1 alpha hydrogen. This one doesn't have any, even though they have the same chemical number of carbon. And also the alpha hydrogen is very important because it's the key step of the metabolic activation. And then with this knowledge, we can also design, modify the nitrosamine by substitute, put substitute at the alpha carbon, or find any nitrosamine without any hydrocarbon. And we also have analyzed all the other chemical classes that I'm not going to talk about because of the time. And well, we have published all this, and this you can find it in the reference. Okay, thank you.
All right, any questions?
Just have a quick question, and this is, are you planning, I don't know how much of this information is already in these in silico tools to predict carcinogenicity or mutagenicity. If not, are you planning to put this or feeding this information into these in silico tools? Which would make, I think, your life probably a lot easier.
Could you repeat the question? What's it?
There are in silico tools available predicting computer programs.
Oh yeah, actually,
right? Yeah.
Good question. Yeah, and we have developed. You can look at the website of EPA. In fact, with this knowledge, we have developed an expert system. We develop knowledge rule and then computerize the rule, and then you can draw a structure and ask whether it is carcinogen, and the system will tell you. We have high concern, moderate concern, low concern, and give you the rationale. Yeah, that's a good question. Yeah, we have an expert system.
It is publicly available?
Yeah, it's open to everybody.
Oh, okay.
Yeah, you can go to EPA website.
Okay, very good.
Yeah, I'll give you the link if you, yeah, later.
At the start, you talked about the genotoxicity and non-genotoxicity. With the first, is the program sophisticated enough to spot the difference between intercalators and groove binders?
Could you repeat your question?
Yep. Is the program sophisticated enough to model groove binders and intercalators, because their structures and their mode of action would have different structure-activity relationships?
Yeah, we since most human carcinogen are shown to be genotoxic, and so we focus on genotoxic. But we also, will also have developed some knowledge rule on non-genotoxic carcinogen, do some SAR analysis.
Yeah, the reason for my question is when you were looking at the aromatic amines and you had one which was almost perpendicular and two were flat, then that really sort of signifies that one could be with the, as like a groove binder, and the others would actually be an intercalator. So that may be a reason why there's a difference.
I don't quite catch your question.
I can speak to you at the break, that's okay.
Yeah, with the in the mic, there's an echo. I think. What? Maybe I will.